So welcome to this week's tutorial 5. So let us see what we have. We'll try to solve a couple of questions which are of relevance with respect to this week's lectures. So question number first is, let us consider a general vector whose base is 0, 0, 0, that is origin, and tip is at any general given point x, y, z, right, in the point group. So the overall environment of the molecule is in, or of the vector is in the point group C2H. I am picking up a relatively easy system, but you can work out similar problems in different point groups. Okay. So how does it look? So you have right-handed coordinate system. So you have x, y, z. Okay. And any given vector where origin is 0 and its tip is x, y, z, right? And you know how to calculate the length of this vector and so on, right? So now let us start with the parts of this question. So this is what you have been given. Now what you have to do is derive the set of 4 3x3 transformation matrices that constitute the reducible representation by which, let us call this representation as tau m, by which the vector v transforms. Okay, so what you have to do is you have to derive a set of 4 3x3 transformation matrices that constitute the reducible representation tau m by which this vector v transforms. So this vector v transforms, what do you mean by that? So origin is supposed to be not changing, so it is supposed to be fixed, and only the vector tip is supposed to be moving under different symmetry operations. So what are the different symmetry operations under C2H point group? So under C2H we have E, C2, I, and sigma H, right? So this C2 is along Z axis, C2Z. So now under each of this symmetry operation, you have to see what will be the transformation matrix so that it will define how vector v will transform. So how do we do that? So this is nothing but the unit vector transformation problem, which we have already learned. So basically what the question is asking is that what happens if what will be the E matrix if I transform x, y, z? So this vector v can be written in terms of a column matrix x, y, z, where x, y, z are the coordinates of the tip of this vector. And what happens to this after I transform it using E? So E does not do anything. So x, y, z remain as x, y, z. This implies that E is a unit matrix of order 3. So what I have is 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is my transformation matrix. Okay. This can also be called as transformation matrix. So similarly, we have to calculate all the transformation matrices, all 4 transformation matrices, which will be 3x3 order. Okay. So because we are in XYZ system, so that's why this will be 3x3 order. So basically the dimension of the space in which we are, it's a three-dimensional space. So that's why this will be 3 cross 3. But this can be multi-dimensional. This can be lower dimensional than 3. So depending on in what dimension we are working, the order of the matrix will change. Okay. So now let's do the same thing for C2Z. For C2Z, if I operate C2Z onto the tip of the vector, that is my XYZ. Now understand that what happens to X. So if I go back to the picture here, so if I do a C2Z operation, so my C2 is lying along Z axis, my X axis moves to minus X, Y axis move to minus Y, Z remains at Z, right? So that means this vector will change its coordinates as minus X, minus Y, Z. Okay, so now let's write it down here. So this is the resultant vector, minus X, minus Y, and Z. So this implies C2Z can be written as, so now you have to imagine a matrix which would multiply with XYZ to give you this, right? So you must be very thorough with the matrix multiplication. So now I understand that if I multiply minus 1 with X, I will get minus X, right? So that means it will be minus 1 here. And since X is remaining as X, there is no other component in place of Y and Z, so it will be 0 and 0. Similarly, Y is multiplying with minus 1 to give you Y. Suppose if there is a X component or Y component or Z component, then I will have some numbers here also. But since there is no X and Z here, only Y, so that means I will have minus 1 here and 0 here, right? Now for Z, again, this will be 0 and 1, right? So this is my transformation matrix for C2Z. So you can also write the similar thing for general. So in general, we can say, let's write the general one, CN Z. So any CNZ matrix can also be written as that we have already calculated. So mind you that the rotation here will be anti-clockwise rotation, because if you are using clockwise rotation, the result will be different. So this you have to keep in mind, that all the rotations that we are doing in this class are anti-clockwise. So cos theta minus sin theta 0. Then I have sin theta, cos theta 0, 0, 0, 1. So Z does not change, so that's why plus 1. Now if I put 180 degree, cos 180 degree will be minus 1. So for C2Z, I can say theta is equal to 180 degree, right? So this will be 2 pi by 2. Okay. So if it is 2 pi by 2, you will have 180 degree, or I can say 2 pi by n, where n is equal to 2, right? So because theta is 180 degree, my cos theta is equal to minus 1, sin theta is equal to 0, sin theta is equal to 0, cos theta is equal to minus 1. So I get the same matrix here, right? So either you use the general formula, or you actually do the transformation on X, Y, and Z and see where they are going. Either way, you should get the same result. So this is my transformation matrix for C2Z. Okay. Now let's write down for I and sigma H. Now if I do I operation on X, Y, Z, by definition, I should flip all the coordinates. So I should get minus X, minus Y, minus Z. So now the vector basically is moved to the opposite quadrant in the three-dimensional space. So X goes to minus X, Y goes to minus Y, Z goes to minus Z. So that means I is again a unit vector, but with all ones as minus 1. 0, 0, minus 1. Right? Now for sigma H, so if I do sigma H on what will be the orientation of sigma h? That is important to understand. So by definition, it's a horizontal plane. Horizontal plane has to be perpendicular to the principal axis. Principal axis is C2Z here. So if perpendicular, if C2Z or principal axis is lying along Z axis, so that means my sigma h will be lying along XY, right? So if sigma h is lying along XY or XY axis are lying onto the sigma plane, they will not change their sign, right? So X remains as X, Y remains as Y, and Z changes its sign to minus Z. So if we go back again here, so if this is my sigma, my XY will not change. The Z actually goes down to minus Z. So that's how it changes to minus negative Z, right? So once you have identified the final result, all you have to do is now identify what will be the matrix which will multiply with XYZ to give you XY minus Z. So now that is simple to find out because X is multiplying with 1. So there is no Y component, there is no Z component in this column, in this row. So again you have 0, 1, 0, 0, 0, minus 1. Now, so my set of transformation matrices or my reducible representation I can write as C2H E C2I sigma H. Now this is my tau m, which is the reducible representation. So I will say this is my, which the question asked, right? Reducible representation consisting of 3 cross 3 matrices. So this is my, so for C2 I have minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. For I have minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. For sigma h I have 1, 0, 0, 0, 1, 0, 0, 0, minus 1. So this is my tau m, which is reducible representation. So that's how, so you can also call it as set of transformation matrices under which vector V will transform in C2H point group. Now next part is reduce the tau m into component irreducible representations. So we now know what is a reducible and what is a irreducible representation by block diagonalization of the matrices. So now what you have to do is you have to block diagonalize these matrices. So what do you mean by block diagonalize? So what we have to do is we have to see if I can find out only diagonal elements. So block diagonalize means that only diagonal elements matter and rest where the elements are 0, it does not matter. So I can see that this is my first element and this is my second. So rest other elements are 0. So this is the diagonal which is already block diagonal. So similarly, and it has to follow in all 4 matrices, right? So suppose if there is a number here, let's say if there is a number 1 here, okay, in that case I would not be able to consider this minus 1 and this minus 1 as block diagonal. In fact, I will have to consider this 2 cross 2 matrix, and if that happens I have to consider the 2 cross 2 matrix in all 4 cases. Okay, so because it is 0 in all the cases, I can consider 1 cross 1 matrix in all of them as block matrices. Okay, so I will just write 0 back again. So we have already discussed what is block diagonalization. So once you do this, now I can say that this matrix representation or this reducible representation tau m can be written as tau 1 plus tau 2 plus tau 3. Okay, so what do you mean by that? Where tau 1 is nothing but, I will write first component here, 1 minus 1 minus 1 1. So 1 minus 1 minus 1 1. So this one coming from here, this minus 1 coming from here, minus 1 coming from here. So respective elements of all the matrices basically. Tau 2 again 1 minus 1 minus 1 1. So these two are same, there is no dot here. So for tau 3, this is now the third element, which is 1 1 minus 1 minus 1 1 1 minus 1 minus 1. Okay, so now if you notice, or let's not discuss that because we have not discussed Mulligan symbols yet, so we'll do that later. Okay, so these are the set of irreducible representations for C2H point group. All right. Now, what is the next part of this question? So this is, so write the reducible representation of characters of tau m matrix representation. Okay, so what do you mean by writing tau m, writing the characters of tau m matrix representation? So characters means nothing but the sum of the diagonal elements. Okay, now these sum of the diagonal elements are nothing but called as trace or character. Okay, trace of the matrix or character. So how do I write? So let me just look at these matrices. So what I will have is tau, let's call it as tau v. Tau v is, so if I sum all the diagonal elements here, what do I get? 3, this will be minus 1, this will be minus 3, this will be plus 1. So I have 3 minus 1 minus 3 plus 1, right? So these are the set of characters which are obtained from summation of the diagonal elements of the matrices. Now this is also called as a reducible representation because this can be reduced into these ones. Reducible representation of C2H point group. As we know that there can be infinite different numbers of reducible representations. So this is one of the infinite possibilities of reducible representation under C2H point group. Okay, so that should be clear. So now let's move to second question. So now let's consider 3 p orbitals px, py, pz, which are degenerate for an isolated atom. Let us call that atom as M. So if you have an isolated atom, the 3 p orbitals would always be degenerate if there is no ligand or there is no surrounding atom to it, right? So p, by degenerate I mean that they will have equal energy. So by symmetry, they are forced to have equal energy. They are identical. So px, py, pz orbitals would be identical to each other, and thus they will be degenerate in energy. They will have same energy. But now what happens if M is surrounded by several X atoms? The degeneracy of p orbitals is lifted. So if degeneracy is lifted, can we use symmetry arguments to say in under what molecular shape the symmetry forces some of the orbitals to remain degenerate or separate from the other orbitals? Okay. So by consulting the appropriate character table, by consulting the appropriate character table, describe the degeneracy of p orbitals in following molecules. So now you are given some molecules and you have to describe whether the p orbitals will be degenerate or not. Okay. How do we do that? By looking at the character table. So let us start looking at that. So the first molecule is MX2 linear. So, but we should know which character table to look. Okay. So for MX2 linear, what will be the molecular shape? Molecular shape is like this, right? What will be the point group? Point group will be D infinity H. Okay. Now, this is my point group. Now, what you have to do is in the character table, there are several areas in the character table. Okay. That we will learn maybe in the next class. So if you see character table D infinity H, this area will be the symmetry operations listed, various characters are listed, Mulliken symbols, for IR representations are listed, and here is the basis unit vector rotation as well as translational. So that is X, Y, Z and Rx, Ry, Rz are listed, right? And in this area, binary products of unit vectors are listed. Binary products. So now what you have to do is you have to see under this area, this particular area. So how are my X, Y and Z listed? Okay. So let me just write down for one particular example and that will make it clear. So let's go to next page. So for D infinity H, it looks something like this. So there are several lines in the symmetry elements, 2C infinity and so on and so forth. Okay. So infinity C2 and so on. So here again, there are several symbols written. Do not worry about what those symbols are. We will get it clear in the next few classes. Sigma, G minus, and so on and so forth. Okay. So in certain area here, it will be written Z and it will be written here X and Y. So X and Y, comma, and within bracket means that this type of arrangement means that X and Y are degenerate and belong to two-dimensional irreducible representation. So this would mean that any property that also lies along x and y would also be degenerate. So any property that is along x, y would also be degenerate. So z is separate from xy. So suppose if z is also written as like that, so that would mean that x, y, z, all three are degenerate. But that is not the case. In this case, z is separated from x and y. This is purely due to symmetry arguments. So this would imply that px and py orbitals are degenerate in mx2 linear molecule. Okay. So that is very, very simple. Just look at the character table, find out whether x and y are written together within brackets or separately. That would define whether px, py, pz orbitals are degenerate or not. Okay. Now let us see a few more examples. So next example is mx2 bent. So mx2 bent. So how would the molecular shape will be? This is like a water molecule. So you have mx2, the point group is C2V. So now if I refer to the C2V character table, it gives like, so you have Z here, then X and Y in three separate rows. Okay. So Z corresponds to some IR representation, X and Y corresponds to some other IR representation. So that means X, Y, and Z are not equivalent to each other. That would imply that Px, Py, Pz are not degenerate. There can be accidental degeneracy, which is a separate thing, but because of symmetry, you can argue that because of symmetry arguments, Px, Py, Pz are not degenerate. Okay. So this is for mx2 bent. Okay. Now let's look at more examples. What is mx3 trigonal planar? So if you screw up here in the point group, determining point group of the molecule or the shape of the molecule, then you will get a wrong answer, right? So if it's a trigonal planar, how the molecule would look like, this will be like BF3. All of them are in one plane. So that means the point group is D3H. So for D3H, what I have here is X, Y, and Z are in separate rows. So that means only Px, Py are degenerate. Z is separated from Px and Py, right? So very, very simple, but very important application, right? Just by looking at symmetry, you're saying something about energy. mx3 pyramidal. So mx3 pyramidal is like ammonia. So you have, so this will be C3V point group. So under C3V, Z coming here and XY coming here. So this also implies Px and Py are degenerate, right? Okay, let's look at more molecules. You have mx3 T-shaped. Now what will be the point group of this T-shaped molecule? Let's draw the molecule first. So you have M, X, X, x. So try to work out this thing as a home assignment. So I will leave some of those examples as home assignment. So you have mx3 t-shaped, then let's increase it, mx4 tetrahedral. So all you have to do is just find out what is the point group, look at the character table, look at the unit vector transformations, whether it is transforming together or separately. If it is together, it is degenerate. If it is not, it is non-degenerate. So very, very simple. So tetrahedral, mx4 can also have square planar, can also have irregular tetrahedral. So this example we have not discussed, but I would like you to find out what is irregular tetrahedral and what will be the point group of that. Okay, so mx5 square pyramidal, then trigonal bipyramidal, and last will be mx6, which will be octahedral. Find out how the symmetry of p orbital changes, whether they'll be degenerate or not, in all of these shapes. Okay, so I think that will be all. Next class we'll discuss more problems. Thank you very much.